Hello everyone, today in this video we are going to study the conduction heat equation, and our primary objective in conduction analysis is to obtain the temperature distribution which allows us to calculate the conduction heat flux at any point using Fourier's law. This involves defining a control volume, applying energy conservation principles, identifying energy transfer processes, and solving resulting differential equations with proper boundary conditions. We start by considering a homogeneous medium without bulk motion, expressed in Cartesian coordinates. Here the temperature distribution is T as a function of x, y, and z, and we define a controlled volume, delta x times delta y times delta z, and by applying energy conservation with only considering thermal energy forms, we can identify the energy transfer processes. The energy storage, which refers to the change rate of thermal energy within the system, equals the energy inflow minus the energy outflow plus the energy generation within the system, which represents some energy conversion processes that involve generating heat. It could be chemical reactions or any other sources. Now, the energy inflow minus the outflow is represented here as the heat transfer rate of x minus the heat transfer rate of x plus delta x, which is simply the outflow from the other side. Also, the heat transfer rate of y minus the heat transfer rate of y plus delta y. And finally, in the z direction, we have the heat transfer rate of z minus the heat transfer rate of z plus delta z, in addition to energy source. And as we know in thermodynamics, the change of thermal energy within the system equals the isoperic heat capacity, Cp, times temperature differences. The isoperic heat capacity, Cp, can be written as mass times the specific isoperic heat capacity, which is usually denoted as small letter Cp, which means that it is divided by mass. And we also know that density is mass over volume. Thus, we can write the mass as volume times density, where in our case, volume equals its small increments, delta x, delta y, delta z, and by dividing the time interval, delta t, we obtain the rate of thermal energy change within the system. Also, we have previously seen the relationship of the heat transfer rate per unit area, or what we can call it as heat flux for simplicity. So we can write our heat transfer rate as a product of the heat flux and the surface area, which is the cross-sectional area delta x times delta y, and so on for the other two directions. Noting that heat source is represented here as the volumetric heat generation times the volume. Now we can rewrite this equation by dividing both sides on the finite increments and rearranging the terms. However, according to the definition of the derivative, we already know that the derivative of a function fx equals the limit of fx plus delta x minus fx, all divided by delta x, and that's when delta x approaches 0. So by applying the definition of the derivative to each term involving heat flux, we obtain partial derivatives with respect to the spatial coordinates, and these partial derivatives represent the change rate of heat flux with respect to each spatial direction, providing a continuous representation of the heat transfer equation. Finally, by substituting Fourier's law into our previous equation, we obtain the general form of the heat conduction equation in Cartesian coordinates. And this equation states that at any point in the medium, the total rate of conduction heat transfer plus the rate of heat generation must equal the rate of thermal energy change stored within the volume. So this is the heat conduction equation, or diffusion equation, in Cartesian coordinates, and for its solution we can determine the temperature distribution as a function of time. To find the temperature distribution in a medium, solving the heat equation is essential. The solution depends on the physical conditions at the boundaries. Because heat equation is second order in spatial coordinates, two boundary conditions are required for each coordinate. And because it's first order in time, only one initial condition needs to be defined. However, there are three common types of boundary conditions. Boundary condition of the first kind, or Dirichlet condition. This is when the surface stays at a constant temperature. Boundary condition of the second kind, or Newman condition. Here, instead of a constant temperature, we have a constant heat flux through the surface. The third kind of boundary condition involves convection heating or cooling at the surface. This means heat is transferred through the movement of the fluid, and we can write the energy balance equation between conduction and convection from the other side. In another word, Fourier's law of conduction equals Newton's law of convection. So these are the boundary conditions which help us solve the conduction equation. That was all for this video. Thanks for listening, and see you in the next tutorial.